Okay, good morning. Just a brief biography from Professor Scaglione. Professor Anna Scaglione is currently a professor in electrical and computer and energy engineering at Arizona State University in the US. She is IEEE Fellow since 2011. Her research spans several disciplines from signal processing, communication networks, control and power systems. In the area of power systems, her work focuses on data analytics for intelligent and secure energy delivery systems and flexible demand modeling for their optimal integration into energy markets. She received the 2000 IEEE Signal Processing Transaction Best Paper Award, and in 2013, the IEEE Donald G. Fink Prize Paper Award for the Best Review Paper in that year in the IEEE publications. And the work with her students has received several conferences and one earned 2013 IEEE Signal Processing Society Young Author Best Paper Award. And if I'm not mistaken, you are a distinguished lecturer of the IEEE Signal Processing Society as well. So we are delighted to have you here, Anna. Please join me in welcoming Anna.
Thank you. So this is going to be a little bit of a marathon. I hope I keep your attention alive. So we have 4 parts of this talk that should be roughly 50 minutes. The third part, which is the juice of the talk, will take perhaps a little bit longer, so I may start it while I finish part 1 in the second slot. So I start from scratch. I'm assuming even very little knowledge of probability and stochastic modeling. But I have to warn you, this is going to be a shower hose. So if you want to deepen these notions, please look at the slides and look at the keywords, and you will find plenty of material that will supply more fundamental and more extensive knowledge. The fourth part is really focused on modeling for power engineering. The first 3 parts are sort of textbook material, so let's get started. Okay, so modeling the data. So first of all, let's discuss what are the goals, the general goals of machine learning. In general, we want to transform data into a description. So X are the data that are given to us, and Y is what we want to infer. And this description can be a class. In that case, we call it classification problem. This would be the type of decisions that we want to make. And what you see here, there is a red dot, which is our inference after having trained our classifier on these other data. And the data are little stars or little X's, just they denote data that are labeled. So these are the training data. And the rule here, you can see, is parameterized by the parameters of this straight line. And you can encode the rule that gives you the label, if you call this the positive region and the negative region, as the sign of this half plane. So you evaluate X, and that gives you the new prediction on the label. The other problem is the regression problem. So in this case, it's one-dimensional. X is one-dimensional, and you're trying to predict what Y will be. And again, you have training data. And in this case, you decide that your model could be a linear model, and you do a linear regression. So in both cases, these theta are the parameters that you want to learn, right? So machine learning is about learning the model and then applying that model for an inference. And so you could actually potentially, and a lot of machine learning algorithms have been developed that now just sort of forget about statistical modeling. They try to directly find a function in a function class that they can use later when new data come in to predict, again, your representation. Y could be a class or a continuous value. And in general, you're not necessarily going to always utilize directly the raw data. You may extract features that are relevant and informative about the quantity you want to perform a regression on. So in this case, for instance, if you want a quadratic model, you can conveniently express Y also as the inner product of theta, which is this vector of parameters, and these coefficients that are essentially the powers of x until 2. So you can see that this model is relatively simple in the sense that it's linear in the parameters. It may be complicated in the data, but it's linear in the parameters. So how do you formally describe the deterministic parametrization? You say you have a function class, and then how do you pick the function out of the function class? You describe a non-negative function which describes your loss in not finding a good function. And typically what you do in deterministic algorithms, you sum the loss over the training data. And so you're trying to minimize this cost, and this parameter gives you the best fit according to this approach. But the question with deterministic formulation is that really these are heuristics. And oftentimes the heuristics that are applied uninspired by famous statistical models, which is what we're interested in. So compared to the deterministic case, you are not trying to learn this mapping directly, but indirectly. And this theta parameter is really something that depends on your model, your statistical model for the data, right? And in general, when you study Bayesian inference, what you have is you assume you already have this model. But just like in the case of the deterministic machine learning algorithm, you need, in fact, to derive this model from training data, okay? So a lot of algorithms that I'm going to discuss assume that I have this, and in particular Bayesian network and graphical models that will go into a Markov random fields, they will assume you have these probabilities. Why? Because those are directly giving you this rule. But then I will talk about how do you fit these to training data. So because we need to have a stochastic description, I want to talk a little bit about random experiments and probability, right? And I will jump, instead of talking about one random variable and one simple random experiment, I will jump directly describing a random experiment as giving you some vector of data, right? And in general will be the vector that includes in the training data y, but later on you want this model where in fact the part that is instantiated is this data that you use for an inference, right? So you can imagine you're taking a snapshot and the gray level of this face are form a list of pixels, and the list of pixels is organized as a matrix, but it doesn't matter. All the values are your vector of data. And what do you do, right? So this is the first step of a course on probability. You first of all have to model what is possible, and that will be the sample space. And since you have an experiment that returns a set of numbers, right, a vector of numbers, this will be the Cartesian product of the sample spaces of each of these values. And oftentimes, the sample spaces, the outcomes that are possible for each entry of the vector are the same. But if you include the representation y, if the representation y is discrete, and instead you have a continuous pattern, then in that case they're mixed, right? So let's call S the sample space, which is the sample space of this tuple of values. Then after that, you have to provide a measure, a number that tells you how uncertain, right? How likely is your bet to be won, right? If you bet on a certain value. And the typical approach to do that, there has been a lot of philosophical debates on how to do it. And in fact, you will have to have some kind of approach to train your model. But let's say that in terms of modeling a random experiment, this step is based on finding a law that satisfies these three particular axioms. So it's an axiomatic approach. All the theory of probability is derived based on this axiom. And what the axioms say is they specify something about events that are just a subset of outcomes. And they say that the probability measure should be non-negative, that the probability of having something that contains an outcome out of all possible outcome is certain, right? So that's a certain event, and that is 1. And in general, anything that is certain will have probability 1. And it is sufficient to also tell you that the probability should also be greater than 0. And then there is this other important law, which here establishes the additivity of the probability of the union of two events. But that's not true in general. It's only true if these events are mutually exclusive, which means that essentially they don't have any outcome in common. So you cannot see these events happening simultaneously because they have no outcome in common, okay? And in general, if this intersection is not empty, you will have the subtraction here of another term, which is the probability of the intersection of the two sets. So that's why we say that these laws are subadditive, right? And the axiomatic approach relative to when in the 1500 probability was invented is relatively recent. It's 1933, so we have made quite a lot of progress. So how do we assign a law? So now, for a moment, let's consider one single random variable. Random variable simply means the experiment is associated to some number, right? So in the case of discrete outcome, so if there are only discrete number of things that can happen, you can assign a number between 0 and 1. And so we call it a mass of probability, and correspondingly this law is the probability mass function, right? What is a function? It's a function that is expressed for every x. All of these probabilities add up to 1 because they have a certain event, and this is a very simple assignment. It's a little bit more complicated when you have density, when you have continuous random variables that take any value in an interval, because you cannot assign a finite probability to all of them. Otherwise, if you add them up, you will never get something that adds up to 1. So what you assign is a density of probability, something that if you integrate in a particular interval that is contained in the sample space or has some overlap with the sample space, then you get the probability that the outcome will be included in A. And in particular, you could equivalently assign what is called a cumulative distribution function, which is the probability of every open interval. And in fact, these are two equivalent assignments. So you could assign this because essentially the density is just a derivative of this, right? And with this, you can describe any probability for any event that lies in the sample space. Since we are interested in vectors, effectively we are interested in joint events. So let's start with two random variables. If you understand two random variables, you understand n random variables, right? So because you step from single variate calculus and series to essentially multivariate already if you have two, right? So it's no big deal. So in this case, let's say you have two random variables, so you have to describe a joint probability mass function, which is the probability that you have for one value x a particular outcome or instantiation, and for the other value of y, these other ones. So they both have to happen, right? The probability that both happen when you run the joint experiment. And from this, you have more information than you have from the probabilities of x and y individually, because you can calculate the marginal probability by adding up all the possible values. Sorry, here should be of y, and here should be of x. I mixed up these two indexes. So you have to saturate all possible values, which means anything can happen for y, but only one outcome can happen for x. Okay? So in general, for L particular random variables, you will have that you just put this comma, but what you mean, this is the probability that the first random variable is 1, and the second is 2, x2, and the nth is L. And the joint probability mass function, therefore, is the generalization of the 1 for 2. So there is this language that is used, often it's called marginalizing. Marginalizing is very important for Bayesian networks, so it's important that we understand each other. So if I have, again, now a vector that has 4 entries, it's a random vector, and I have the probability mass function for this vector, this 4-dimensional vector, then I can obtain not only the marginal with respect to each of them, but I can obtain probabilities of a subset of the entries, right? And these are a lot of operations. There are 2 to the 4 possibilities, so I can derive all these other joint statistics from the joint statistics of the entire list that is my vector. But more importantly, for Bayesian network, what will be crucial is the notion of conditional probability, and this depends on the result that was obtained by Bayes, right? So he codified this law, and what he proved is essentially that if you have observed a certain vector x, in this case it could be your pattern, right? the probability that you have a certain outcome for y is equal to the joint probability of those two outcomes normalized by the probability of x, right? So if you have provided a joint probability, that is sufficient essentially to describe another probability law, which is the probability of the conditional event. Now, this law is symmetric in the sense that you can define also a conditional probability of x given y, right? And is defined similarly, just you have to normalize now by the marginal of y, which is the marginal of the conditional event. Also, conditional probabilities are a way of factorizing the joint probability in multiple terms. And so you can, again, utilize this law or this law and break it up in these factors. From that theorem, some useful notions come. So if, for example, for you it's easier to assign a conditional probability, you can actually recover the marginals, not saturating the joint, but this is a joint probability if you think about it. So you can utilize directly the conditional probability, and this goes by the theorem of total probability. So it's a way of recovering and marginalizing the distribution through the conditional. And there is also this rule, which is called Bayes' rule, which allows you to flip the conditioning. So if you have the conditional probability of x given y, you can utilize the theorem of total probability here to calculate the marginal of the conditioning event, and then you can obtain the probability of y given x, right? And again, I utilize this notation on purpose because as we define our machine learning task, y is the description, x is what you're going to observe and what you want to make a prediction on. This is kind of your latent variable in your observation model, not in the training data, but in your observation model. And so we call this the posterior probability because it describes what is the probability of your label or of your latent variable given what you have observed. Okay? Now we can generalize this rule and factorize the probability of L random variables with what is called the chain rule. So this is recursive. We condition to a stream of random variables which contains all of them except one, and then we look at the probability, joint probability of the conditioning random variables and do this again until we arrive at a marginal. And here the order doesn't matter. I mean, it doesn't have to be in this order. Okay. Now, things that are really useless if you are you're trying to face an inference problem is when your observation is independent of what you're trying to infer. So the notion of independence says essentially that the conditional probability of one random quantity given the other one doesn't change. It remains the marginal. Or in other words, the factorization that you have for the joint probability is the product. And for a vector, if all the random variables of this joint experiment are independent, you have the product of the probabilities. But what really is essential for Bayesian networks is generalizing these, which is the most trivial case, and leveraging independence, another form of independence, which is called conditional independence. So now let's imagine that we have three random variables. So let's call them x, y, and z. So instead of x1 and x2 and y. So we say that x is independent of z given y, right? If this is true, so conditioning on y and z is equivalent to conditioning only to y. And as a matter of fact, the conditional probability of x given y and z is just a conditional probability of x and y, right? And in this case, the chain rule looks similar, but the real difference here that instead of conditioning this term on x and y, this only depends on y, right? And this actually becomes a great simplification because to exhaustively describe this probability or do computations, now this term only depends on two variables and this depends only on one variable, and that's very, very useful, as we will see. So the joint PDF, you can integrate any interval. You can actually interpret this, sorry, this should have been multiplied by the x times the y, right? So the density multiplied by the infinitesimal area is a probability is the probability that you are in a small interval around the point x and y, right? And if you look at the marginal PDFs, you can obtain them by saturating everything with respect to the other variables. So the marginalization works the same. For a joint PDF, this is kind of unreadable, but it essentially is the same thing. Now the interval, though, it's a tiny n-dimensional interval in the L-dimensional space, real space. And you can marginalize in the same way, except now you have to perform integrals. Bayes' theorem also holds for densities of probability. Again, these are not probabilities, but you can show that you can actually simplify the element of area or of volume. And so you have the same kind of form where the conditional density is going to be the ratio of the joint density divided by the marginal density. And again, the description is symmetric, and once again, you can utilize this relationship to factorize the joint distribution. These are analogous to the theorem of total probability and the Bayes rule to flip conditioning, as well as the chain rule. They hold exactly in an identical fashion, except now you have to integrate instead of doing summations. And also the notion of independence, it manifests itself through the structure of the density. The conditional density of y given x is going to be equal to the marginal, or you can say that you can factorize the joint density, and for L random variable you have just the product. Okay, so this is exactly the same, and also for densities you have the notion of conditional independence that leads to the same type of factorization. So in classification, what kind of probabilities we have? Actually, it's useful to look at Bayes' theorem also to express these probabilities, because the probability of a class given the observation, the class is a discrete random variable, so we have a mass function, and we can express this mass function utilizing Bayes' theorem as the product of the density of the observation given y times the probability mass function of the conditioning event divided, by the probability mass function of x, right? The density of x, okay? And the density of x can be obtained saturating again over all possible y's, and you can saturate using the theorem of total probability. So the only difference between this case and the previous cases is I have a mixed event, right? So I have a mass for y and I have a density for x. In regression, instead, we are dealing always with densities, right? I have the density of y, this is a continuous variable, and this is expressed as we said before. So I say great expectations. Why? Another important thing to remember about probability are what are expected values, right? So these are numbers that are associated to a particular probability mass function or a density function that characterize essentially in a less detailed fashion properties of the random variables. And they're very important in Bayesian learning because typically you are now trying to minimize an expected loss or an expected risk or maximize the probability of being correct, right? So these are something that you can, in many cases, express as an expectation. So in the case of the error rate, really this is not something that needs expectations. This is a conditional probability. The probability that you mislabel a certain value y, given that the true value was y. But all of these other measures are going to be expectation. One is the so-called Bayesian risk. You attribute to the decision, each decision, so each association between a label and an estimated label, a certain risk. And then what you care about is to find the detection rule that minimizes this risk, the expected risk. We also care about other two measures. These are recurrent measures. They're not the only one, but they are the more recurrent that we use. We care about the bias, so how different is the expectation of your inference relative to what you want to infer, and the mean squared error, right? Which measure on average how far you're going to be from y, and the square difference is essentially penalizing big error. So you want to minimize it because you don't want this to grow. And so what this function that we try to find in Bayesian inference is, this theta hat, which is the parameter that essentially is the distribution, right? Is obtained directly by trying to minimizing this cost. And so as you can expect, it will depend on the distribution because these expectations are nothing but integrals or summations of these values over all possible outcomes. And so these are the definitions. The expectation of x is just for a discrete random variable, the summation of x times px. This is the integral. The variance is the mean square deviation from the expectation, right? So you basically recenter the value and try to understand how large is this difference. So this is going to be large if your probability mass function or probability distribution are very spread out, and it's going to be very small if instead they are concentrated around the mean. And you can generalize this notion putting any function g of x inside of the expectation. That's why it's so handy, right? G of x could be your loss. And there is this particular relationship that is useful. So you can define any moment, which is the expectation of x to the power n. But among them, the mean square is very much used in statistics. And the mean square is simply the second order moment and has a nice relationship with the variance and the expectation, which is expressed here, is the variance plus the expectation square. And so if the expectation is 0, it matches the variance. Otherwise, it's a little larger. Okay? So if your estimator, for instance, is unbiased, then the variance of the estimator would be actually also the mean square error that you have. Now, if you have joint experiment, you want to define what we called higher order statistics. And the first one you study is a second order statistics, which is simply now generalizing the notion of expectation. You take the product of the two random variables and you take the expectation of these products. And you can also define the center moment, right? So you subtract to each of these random variables its own mean. And in fact, you can actually find an extension of the previously found relationship between variance and mean, where you say that this joint moment is nothing but the covariance plus the product of the expectations. And if x happens to be equal to y, you just recover this relationship that we saw before. And in particular, in fact, the covariance of xx is x. And of course, you can also calculate it as an integral. And so one quantity that will appear often, particularly because in explaining Bayesian inference, we oftentimes utilize Gaussian random variables, which we will see depend on this covariance, is a matrix for an n-dimensional vector that contains the covariances of all pairs. So in the diagonal, you have the variances and all the covariances in the off-diagonal. And another quantity that often is used or appears is the correlation matrix, which is nothing but the same kind of definition, but here the random variables are not recentered. Now, there are interesting properties. This covariance matrix, here we are considering real random variables, so it is symmetric. And is also what is called positive semi-definite. That means that basically if you do this product, you have a vector u, you multiply u transpose times u, this product will always give you a non-negative value. And there is a simple proof. You can just, whenever you have linear combinations, you can bring anything deterministic inside the sign of expectation. And so if you do that, then you can essentially discover that u transpose times this vector transpose times u is nothing but the square of this, which has to be always greater or equal than 0. And so the covariance is nothing but the expectation inside, so this is a simple proof. Often recurrent is also the eigenvalue decomposition of a vector covariance. So the eigenvector decomposition exists because this matrix is symmetric. So this is from algebra. You know that there is an eigenvalue decomposition. Not only that, but you also know that here, instead of having the inverse, you have the transpose because these matrices contain orthogonal, U contains orthogonal columns. And the matrix inside is a diagonal matrix, and these are the eigenvalues. And in statistics, oftentimes, the idea of principal components, which actually was introduced originally as a generalization of linear regression for an n-dimensional vector, for a statistical model, you also oftentimes call these eigenvectors, the eigenvectors that are associated to the top eigenvalues as principal components. Now you can define also moments, joint moments of two vectors. So you have the cross-covariance here. You have the cross-correlation. Sorry, here I shouldn't have subtracted this. And you also have that the following holds as well, right? Now an interesting thing is that if you have independent vectors, then their covariance is going to be 0. So this is a sufficient but not necessary condition for independence. So if you find that the covariance of two experiments is non-zero, at least you know you're not in the regime of being independent. So let's make a few notes on Gaussian distributions, which are going to be recurrent in our calculation, because whenever something is Gaussian, a lot of results simplify and appear in closed form. So this is the simple density for a univariate experiment, which is a Gaussian experiment. And the important thing is that these parameters, sigma square and mu square, they are actually the mean and the variance of the distribution. That's why one is called sigma square. And oftentimes, the way of referring to the mean is with the Greek variable mu. Okay? And what happens is that if the variance is large, then this becomes fatter. If the variance is small, this becomes more peaky. And these kind of trends can be found also in the n-dimensional case. So here I'm showing two cases. The difference between these two cases, if you can see here, the level curves would be circular here, perfectly aligned. And this shape is perfectly aligned with the axis x and y. In this case, instead, you can see that this looks more like the fin of a shark. So it's bent, and the level curves are going to be ellipsoid. And the general form of the joint distribution in terms of the random vector, in fact, decreases exponentially as this quadratic form increases. This is the equation of an ellipsoid. Sigma to the -1 is, this, again, is a positive definite matrix in this case. If it was positive semi-definite, you essentially have some redundant variable. So you cannot write it exactly in this form. You have to simplify some of the variables here because they are fully correlated with the rest. And in general, we will use this notation, calligraphic n. Here, this is an abbreviation for saying that x is distributed according to a normal distribution with mean vector mu and covariance sigma square. And oftentimes, I'm just going to refer to the covariance as sigma because it's simply easier. So this is in a drawing showing the level curves of the two cases that I was showing before. In particular, you get the circular symmetry if the covariance is an identity matrix multiplied by the variance of each variable. And in this case, the exponent here can be factorized, and that's an indication of independence. Gaussian random vectors are independent if all the random variables are uncorrelated, and you get these elliptical shapes if that's not true. And in particular, the eigenvectors are nothing but the principal axis of these ellipsoids. Okay? So again, as I said, if they're uncorrelated, they are independent. So for Gaussian, this condition is the covariance equal to 0 is not just a sufficient but also a necessary condition for independence. So it is not only a necessary but also a sufficient condition. And also this other fact is very handy, that if you marginalize jointly Gaussian distribution, you always get Gaussian, right? It's not just the marginal of each random variable, but also the marginal of any subset of the random variables, right? But it's important that the joint distribution is Gaussian, right? So you could have two random variables that have marginal that are Gaussian, but the joint is not Gaussian. It doesn't matter. But when the joint is Gaussian, then any marginal will be Gaussian. Now there is a nice reason to also look at the eigenvectors of the covariance, particularly for the Gaussian random variables, because actually there exists a linear affine transformation. Linear affine means you multiply by a matrix and you add some constant vector, right? A linear affine transformation that if you take a vector x which has a certain covariance and a certain mean, transforms this vector into a vector w that has all uncorrelated Gaussian random variable. And here this uses two facts. One is just a mechanical fact that you can prove that the mean of this random vector is 0 and that the covariance becomes an identity matrix actually in this case, because you have rescaled also by the eigenvalues, but by the square roots of the eigenvalues. But also it exploits the fact that any linear affine transformation of Gaussians gives you Gaussians, right? So these are wonderful because you don't have to make complicated calculations. Typically, transformation of random variables are not very easy, right? Just like any function of multivariate function is not easy. Another fact is that if we try to apply Bayes' theorem, also we find Gaussians. So if I have a vector of Gaussians and I partition it in two parts, then if I try to calculate the conditional probability of x1 given x2 or vice versa, right? So here I'm indicating I and j because this could be 1 and 2 or 2 and 1. Then I get also a Gaussian, so this will be a normal distribution, and it has an interesting structure. The conditional mean is the mean of the original variable plus a term that depends linearly on the variable you are conditioning on, right? So you have to recenter this random variable, then you have to multiply by the cross covariance of the two random variables, which is this off block at the off diagonal, times the inverse of the covariance matrix of the variable that is random here, right? You are conditioning xi given xj. This is the sigma of xj. Not only that, but also the covariance has an interesting structure, is the covariance of the original matrix minus this product. This is, again, cross covariance of x and y, cross covariance of x and y transpose, and the inverse here in between. And actually, you can prove that the eigenvalues of this matrix are always smaller than the eigenvalues of this. It's as if you have kind of concentrated. So the knowledge of y has added, has reduced your uncertainty about x. And that is true as long, of course, as these are non-zero, right? So when those are 0, again, this subvector is going to be independent from the other vector. Now, again, these parameters that I wrote here are also the conditional mean and the conditional covariance, right? Just we know this is a property of Gaussians. So now, if you think about it, if you have this vector that I divide, let me consider my model as a jointly Gaussian model. This is, again, what I want to make an inference on, and this is my observation. If I utilize the Gaussian model, now I have a direct way of calculating the conditional probability of y given x, what we call the posterior. I observe x, what is the probability of a certain label given x, right? So I easily can calculate both the conditional expectation as well as the variance of this, right? Again, this is a regression problem in this case because y is continuous. And you can see here it's clear that I'm subtracting a positive term. So in general, if these are, there is correlation between y and the pattern I observed, then this variance is going to be smaller. So that idea that the uncertainty is reduced by looking at the observation is still true as long as it's not independent. So actually, I want you to look at it a little bit more closely. Now, if I have conditional independence, there is a particular structure that I have to have for the covariance. And this is very important because this is tied with graphical models. So if I want conditional independence, for instance, I have n random variables, and I want to factorize this given a certain set of random variables. Now you see here that I have a summation with, I can express this inner product. Now explicitly I have a summation of terms, right? And each of these terms is weighted by the corresponding ij element of the inverse of the covariance matrix. Sometimes we refer to that as the precision matrix, the inverse of the covariance. And so it's clear that if I'm missing some of these products, so if some of these entries are 0, right, then I can exploit the fact that the exponential of a sum is the product of the exponential to factorize the expression, right? So as long as I have the entry 1, 3 here of the covariance, which is equal to 0, then this type of conditional independence holds. So what comes next? Right? It's a perfect ending. We have defined what is an experiment, a random experiment. I try to emphasize posteriors. So in the second part, we are going to introduce Bayesian inference. Okay? And then in the third part, we're going to talk about graphical models, and in the last part, about sort of modeling as a Markovian process power systems.